Hello, I'm Ross Church from Lund Observatory in Sweden, and I'm going to be talking about the role of close stellar encounters in sculpting the stellar population at the very centre of the Milky Way. This is work being led by Alessandra Mastrobuono-Battisti, who is a researcher with us here in Lund, and other people involved are Melvyn Davies and Abbas Askar. This is a short talk, so the bottom line is that the stars that form the galactic nucleus of the Milky Way are old. They're the descendants of a relatively massive population, and there's still a lot of mass there, more than the most massive globular clusters, and they're relatively dense. And these are observational results, but the consequence is that this is a population which is interactive, by which I mean that we expect that the stars will from time to time collide with one another, and this happens frequently enough that it may be able to change the population of stars that's visible at the centre of the Milky Way. So there's observational evidence that the background stellar population is cusped, but that if you look just at the bright giants, which in this case are probably the descendants of stars between 1 and 3 solar masses, that they seem to have a chord profile, and that could be a consequence of stellar collisions changing the population. So we wanted to look into that, and when you have stellar collisions, you can also make weird things, and some of those weird things might be close binaries that could then potentially be detectable by LISA. So that's a sort of speculative add-on to the main material I'm going to talk about here. So we're here making a background assumption that the Milky Way nucleus stellar cluster has been assembled. That is, that it was formed from constituent globular clusters that have accreted into the centre and merged. This is work that Alessandra has done over a number of years, looked at the effect of globular clusters whose orbits decay into the centre and who then merge to form the nucleus stellar cluster. And she's shown, there's a paper here from 2014 that she's first author on, and there's other work in the same series, that if you make a self-consistent n-body model of this, that your resulting cluster, the resulting cluster that she produces, has properties that match the nucleus stellar cluster of the Milky Way very well. The challenge is that this is a massive enough population that you can't do direct star-by-star n-body. You have to do it with superparticles that represent around 1,000 stars. So if you want to look at interactions between stars, you need to do something else. So what we've done is taken those simulations and painted a stellar population effectively on top of them. So one can get a handle for the interactivity of this population by calculating what I've here called gamma sun, which is basically what one gets if one assumes that each of the stars in the population is the sun, and then integrates the expected collision rate given the velocity dispersion and number density of stars in the population. And that gives the plot that you see here on this slide. The x-axis shows the projected galactocentric radius of each particle in Alessandra's simulation at the present day, and the y-axis shows this interactivity parameter. And you can see that for particles that are in the central point view parsec, you expect there's a significant probability that they've undergone an interaction. So in order to test the effects of these interactions, one has to include a lot more than this. There's obviously an initial mass function, there's evolutionary history for that population of stars, and a correctly integrated collision rate throughout the star's lifetimes. And the and then also prescriptions for the effects of different sorts of interactions. And a skip over all of that, you'll find that in Mastrobuono-Battisti et al. In PrEP when it makes it onto the archive this autumn. But what I'm going to show you is our current thought on what one gets if one naively applies such a prescription to Alessandra's current model. This figure shows, as a function of initial mass, various populations of stars that we expect in the cluster in the present day for relatively interactive particles. And you can see if this was a completely non-interacting population, what you would see here would be a single line. On the left-hand side of it, it would be blue. Those are stars that are still on the main sequence. There'd be a brief red bit in the middle, which are stars on the red giant branch today. And then at the right-hand side, the most massive stars have evolved today, so they would all be white dwarfs or neutron stars off the right-hand side of this figure. And looking at this, that's broadly speaking what we do see, that actually the depletion of giants that we get by stellar collisions following our default assumptions is actually small. The population broadly remains the same. The predominant effect, incidentally, is that low mass main sequence stars merge with intermediate mass main sequence stars and cause them to evolve a bit earlier than they would otherwise have done so. So when you look today, the population of stars that would be red giants today is primarily depleted by their ancestors having increased in mass by collision and hence already evolved into white dwarfs. So you might think that this is a null result, but I'm not convinced that it is, because there's a lot of ingredients that we've not included in this model. So things we're looking at are the history of these stars before the clusters made their way into the galactic centre, because actually globular clusters are somewhat counterintuitively more interactive than the nuclear stellar cluster that they produce in the end. One of the things limiting the interactivity is actually the presence of the supermassive black hole, and in Alessandra's models we assume that the supermassive black hole has been there from the beginning of time. But there's a bit of a chicken and an egg question here, and in a separate piece of work which Abbas Askar is talking about in another talk, we look at how the supermassive black hole could have been seeded by intermediate mass black holes brought along with the globular clusters that then form the nuclear stellar cluster. So in that picture, one gets a radically different assembly history for the nuclear stellar cluster, which we're also planning to look into. And finally, there's an assumption underlying this that all the stars are single, but we expect many of them to be binaries, and binaries have a larger collision cross-section than single stars. So finally, there's a question of possible LISA sources, and one effect of collisions is that they can lead to captures. So if you have a giant colliding with a white dwarf, for example, if it hits the outer part of the envelope, it will simply go through, but if it hits close enough in, it can eject the envelope of the giant and you can end up with a close binary. So we want to quantify what the population of potential LISA sources that one can make that way is, to see if there's anything quirky that you don't get in typical populations that it might be interesting to look for. So if you have questions about this, you can contact me by email. My email address is here on the slide, or you can wait for the paper, which should be arriving on the archive in the autumn. Thank you.